Hey everyone, in this video we're going to go over exponential growth and decay. In exponential growth and decay occurs in many natural phenomena. Quantities grow or decay at a rate that is proportional to their population size. So meaning the rate of growth of a particular population is proportional to the size of the population. So rate of growth, so that's the derivative. And so if we have y equals the size or the amount of the population and t is time, then the rate of growth, right, the population is changing with respect to time. So dy dt is equal to k times the size of the population times y, where k is the constant of proportionality. And so this is what we call a differential equation. In Calc 2, you're going to learn how to solve this differential equation. And the solution to that gives us the formula that we know today. Y of t equals c e to the kt. You may see this in different forms like p equals p naught e to the rt and all those other exponential growth functions. If k is positive, the function represents population growth, and so the formula that you might see in this case is that p of t equals p naught, right, the initial population, and then e to the kt. So you might see this. If k is negative, the function represents population decay, and that one is just usually the c e to the kt function is just that when you solve for k, k will be negative. So let's try an example. The half-life of caffeine is 6 hours. A 16-ounce cup of coffee that contains 200 milligrams of caffeine. So pay attention to your coffee. How many milligrams of caffeine does your particular brand of coffee have? So in this particular 16-ounce cup of coffee contains 200 milligrams of caffeine and is consumed at 8 a.m. one morning. How much caffeine will be in your system by 8 a.m. the next day? So there are two questions here, and then after how long will only 5 milligrams of caffeine remain? So let's tackle the first one. So how much, so with word problems, always focus on the question. So how much caffeine will be in your system by 8 a.m. the next day? So if you consume that at 8 a.m. one morning and then to 8 a.m. the next day, we're talking about hours. So how many hours have passed? So 8 a.m. the next day will be 24 hours. Now the other thing that is mentioned in this problem is that the half-life of caffeine is 6 hours. So what is half-life? Half-life is the time that it takes something, a substance or a mass, to decay to half its original amount. So when you have something, so in this case the half-life of caffeine is 6 hours, after 6 hours you started with 200 milligrams at time 0, so after 6 hours you're going to have 100 milligrams, right? So then the half-life, so let me write this as the definition of half-life. The amount of time it takes a mass to decay to half of its original amount. So one of the things, half-life is time. So it is a measure of time. Sometimes people make the mistake of thinking that the half-life will be the 100 milligrams, right? Half of the original amount is 100, but half-life is the measure of time, how long it takes for the amount to reach half. So let's do this. I think we don't need the equation to do this. We can do it by using a table of values. I'm going to do my table of values over here. So we're going to say T and the amount of caffeine. So we know that at 8 a.m., so we're going to say 8 a.m. is times 0. So at 8 a.m. we have 200 milligrams of caffeine. And then the half-life is 6 hours. So for the half-life of caffeine, 6 hours. So we apply one half-life and we're going to get half the amount that we originally started with. So 100 milligrams. And then we're going to try to make our way to 24 hours. So another half-life, so another 6 hours will put us at 12 hours after. That will be half of the previous amount. So 50 milligrams and so on, right? Another 6 hours will be 18, so 25 milligrams, and then another 6 hours will put us at 24 hours, so that will be half of 25, so 12.5 milligrams. So that means that after 24 hours, so by 8 a.m. the next morning, we would have 12.5 milligrams of caffeine in our system. Now that's just with one cup of coffee. So if you have multiple cups of coffee during a day, you just have to add those 200 milligrams at the time that you took it. So for example, if after even just 2 hours you take another cup of coffee, now you're going to have the previous amount plus 200, and then that changes the way that this will go. Okay, so by 8 a.m. the next day, we're going to have 12.5 milligrams of caffeine in our system. Notice that we did not need the equation in this case because our half-life of 6 hours is a factor of 24. So we could just go by factors, but for the next one, after how long will only 5 milligrams remain? So now we do need our equation for exponential growth and decay. So let's look at our equation for exponential growth and decay. Will be, let's see, y is equal to c e to the kt. Because we're dealing with decay, we should expect the value of k to be less than 0 because we're dealing with exponential decay. So when we solve for k, we should see that it's a negative number. So if we're going to use the formula, let's start with some things that we know. So t and y. Now that I'm using this formula, so at t equals 0, y is 200 milligrams. Right? So then what this tells me then is I'm going to have 200 equals c e to the k times 0. But anything to the 0 power is 1, so this just gives me 200 is equal to c. So my equation now is y equals c, right, 200 e to the kt. And a shortcut way of thinking of this is that c is the initial amount. And the reason that I call it a shortcut is because knowing that c is the initial amount, it skips us having to do this step. And so now this is my equation, y equals 200 e to the kt. Now let's bring in the half-life. So when t is 6, right, the half-life is a measure of time, so 6 hours, we're going to get half of what we started with, 900 milligrams. So let's take that with our new equation. So that means that when t is 6, y is 100. And so I'm going to have my equation is over here, y equals 200 e to the kt. So I'm going to have y, so 100, equals 200 e to the k times t, times 6, right, using this point. And divide both sides by 200, so I'll get 1/2 equals e to the 6k. And we want to solve for k. So take the ln of both sides, so natural log of 1/2 equals 6k, right? The natural log of e to the stuff is just the stuff, and then divide by 6. So k equals the natural log of 1/2 over 6. And sometimes you may see that people rewrite the natural log of 1/2 using rules of logarithms, right? When you have log base b of x over y, that means you can say log base b of x minus log base b of y. So the natural log of 1/2, we can rewrite it as the natural log of 1 minus the natural log of 2 over 6, using the rules of logarithms. And the natural log of 1, we know it to be 0. So this is just negative ln of 2 over 6 equals k, and which is a negative number. So we did say we expected k to be negative because this is modeling exponential decay, right? The amount is reducing, is not multiplying, is not growing, is getting smaller. So that's our K. So now our equation model, our exponential model, for this particular problem will be y equals 200 e to the k negative ln of 2 over 6 t. So for this particular caffeine problem, this is our exponential model. So now for part A, it asks for how much caffeine after 24 hours, which we already know. We already did it without using the formula. We got 12.5, but let's just see using the formula. How much caffeine after 24 hours? So that means T is 24, so just plug it in. So it'll be y equals 200 e to the negative ln of 2 over 6 times 24. And so put this in your calculator and you should get 12.5 milligrams. If you leave it exact, so if you don't put K into a calculator and get a decimal for ln of 2 over 6, then you should get the exact answer of 12.5. If you do get a decimal for K, just make sure that you give at least 6 decimal places so that you don't lose any significant figures in the approximation. Okay, so part B is asking for how long until 5 milligrams remain. So looking at our table, it's a good idea to have just like a gut check answer, like how long do you think it's going to take. So notice that after 24 hours we have 12.5 milligrams. So 5 milligrams, it's lower than this, so it's going to be more than 24 hours. So I should expect T to be larger than 24 once I solve this. And so here we're looking for how long, so we're looking for T. So our equation is, for this particular problem, right, y equals 200 e to the negative ln of 2 over 6 t. Now we're looking for T, so I have nothing to plug in there. So that means that 5 milligrams, that's an amount. So that's the y value. So then I'm going to have y, which is 5 milligrams, is 200 e to the negative ln of 2 over 6 t, and I'm looking for T. So divide both sides by 200, so 5 over 200 equals e to the negative ln of 2 over 6 times t. And how do you get rid of the e? Convert it to a logarithm. So I'm going to have the natural log of 5 over 200 equals negative ln of 2 over 6 times t. And now we want to isolate the t, so divide both sides by this. So dividing, this is a fraction, so dividing by this fraction is the same thing as multiplying both sides by the reciprocal of that fraction. And so here, notice that those will cancel, leaving me with just my T, which is what we're looking for. So it will be negative 6 over ln of 2 times the natural log of 5 over 200, which we can reduce that to 1 over 40, right? 200 divided by 5 is 40. So, and put that in your calculator and see what we get. So we have to be very careful in how you input that in a calculator. If you have a just a regular scientific calculator, make sure that you use plenty of parentheses. And what I got for my T is 31.93. So this is, what was the question? How long until 5 milligrams remain? So we can say approximately 32 hours. So in approximately 32 hours, there will be 5 milligrams of caffeine in your system. So sometimes the question is like, right, how long until you're clear of a substance in your body? And so it really depends on the half-life. Caffeine has a half-life of 6 hours. Ibuprofen has a half-life of 4 hours, and then there are different things, different medications that have different half-lives, and so sometimes it's harder to, depending on the half-life, it's harder for something to go through your system. All right, let's try another example. Let's try this example. A sample of Einsteinium 252 decayed to 64.3%, I think that's how you say it, of its original mass after 300 days. What is the half-life of Einsteinium 252? So this, in case you're not familiar with this isotope, it was discovered and it was named after Albert Einstein because it was discovered after a nuclear test that happened in the Marshall Islands back in before the nuclear bomb in World War II happened. This was just a nuclear test, and so this was one of the isotopes that was discovered in the debris of that nuclear test. And then scientists at Berkeley, who were the ones studying this, discovered it and named it after Albert Einstein. All right, that was a fun fact there. So let's see. So we have the sample of this isotope decayed to 64.3% of its original mass after 300 days. And what we're looking for is the half-life. So we want to find half-life. Now remember, so we want half-life is a measure of time. So we want T when the amount is half of the original amount. Which, do we know, by the way, what the original amount is? No, it doesn't tell us specifically the amount, but it does give us a percentage. So we can say then the original amount is 100%. You have the full amount. So working with our table, I'm going to say at time 0, we're going to have 100% of the amount. And then we know that after 300 days, so now our units are days, after 300 days, you have 64.3%. So what we want is we want to find T when we have half of the original amount. So half of 100% will be 50%. And so even though we don't have actual amounts like milligrams, grams, or whatever units, we do have percentages and we can still work with those as our amounts. And so our equation is y equals c e to the kt. For this model, we have 100%, so it'll be y equals 100 e to the kt. And oftentimes with this, we have a given amount that is going to help us solve for k, and then we have our unknown. So this, once we have k, we can solve either for t or for an amount. In this case, we're solving for t. We want the half-life. Half-life is a measure of time. So let's use the second value. After 300 days, we have 64.3% remaining. So this will be 64.3. You don't have to change the percentages to decimals. You can just leave them, and knowing that the units here will be percent. So 64.3 equals 100 e to the kt. This happens when t is 300. So it will be k times 300, and then solve for k. So I'm going to have 64.3 over 100 equals e to the 300k. Take the natural log of both sides. So I'm going to have the natural log and convert that to a decimal, 64.3 over 100. So just move the decimal over. So it'll be 0.643 equals 300k, right? Applying the natural log of both sides, or turning that exponential to its inverse logarithm so that e becomes the natural log. And then k is the natural log of 0.643 over 300. And now we can rewrite our equation, our exponential model for this particular problem will be y equals 100 e to the kt. K is ln of 0.643 over 300 t. Right, this is our y equals c e to the kt. So this is our exponential model for this particular isotope. And so we want the half-life. So we want to know the value of t when we have 50% remaining. And so let's put that in here. So I want the y, I want the amount to be 50. So 50 equals 100 e to the, and I'm solving for t. And so we get 1/2 divided by 100. And this is pretty standard when you're solving for half-life. You're going to have 1/2 equals really your e to the kt. You may see the book use that shortcut, that anytime half-life is used, we go directly to 1/2 equals e to the kt. And now we're solving for t. And so when I do that, how do I solve for t? This is trapped in the exponent, so I need to apply natural log to both sides or convert that exponential with the base of e to its inverse logarithm. So this is going to be the natural log of 1/2 equals the natural log of 0.643 over 300 times t. By the way, notice that this should be a negative k, and it will be, because when you think about the graph of logarithms, whoops, that was not very straight. When you think about the graph of a logarithmic function, its graph is something like that. It crosses at 1. So anything that is less than 1, for x's that are less than 1, notice that the y values are negative. So everything when you're less than 1 over here, so for t less than 1, our y values are negative. And so 0.643 is less than 1, so the natural log of 0.643 will be a negative value. And so that makes sense. Our k should be negative because we're talking about exponential decay. Now 1/2 is also less than 1, so that's negative. So you have a negative number here equals a negative number. When you divide two negatives, you're going to get a positive, which will be okay, because then our t should be a positive measure, right? We're measuring time. So divide both sides by this fraction. So dividing by this fraction is the same thing as multiplying by the reciprocal of that fraction. And so these will cancel. Oh, both sides. So times 300 over the natural log of 0.643. And you can convert this to decimals, and then in your homework they might actually have you give decimals for k. Pay attention to how many decimals you're asked to give. I would say try to give at least 6 decimal places so that you don't lose too many significant figures in the calculation. So here now everything is gone except for the t. So I'm going to have t is equal to 300 times the natural log of 1/2 over the natural log of 0.643. And you can turn that 1/2 into a 0.5, or you can use the properties of logarithms like we used before to say ln of 1 minus ln of 2. Either way, but in the end we should get a t value. And notice, just as for gut check purposes, right, we're looking to go from 100% to 50%. What we know is that it takes 300 days to get to 64.3%. So that's more than 50%, right? So then our t here should be more than 300 days, right? We have, in order to get from 100% to 50%, we have to go through 64. So 100%, 64.3%, then 50%. So we're going to go initial time 0 to 300 days, so more. So we need to go past 300 days. So going back to our t, then when we put this on our calculator, I got 470.88 let's say to 2 decimal places. But it's time, so let's round it to a whole number, so 471 days. So it's going to take 471 days for this isotope to decay to half of what we started with. Now again, we don't have the full amount, but we have percentages. So we can say full amount is 100%, half is 50%, and so on. And so this examples that I did are deal with exponential decay. Exponential growth is the exact same way. It's just that when we solve, our k will be positive. In the population, the amounts are going higher instead of lower. And so like for this example with the caffeine, right, if it was something with exponential growth, instead of 200, it will go higher, like say 300 or 500. So a good example will be when we were going through at the beginning of 2020 and the COVID pandemic, if we were experiencing the exponential growth. So a good example, if you want to look that up, is go to the CDC and look at the data and see what was the exponential coefficient, right? What was the exponential rate of growth? And then we could make predictions, and that's actually what was being used in order to see how fast things were spreading using an exponential growth model. All right, in our next video, we're going to do some fun problems involving Newton's law of cooling.